Welcome to a new video in this tutorial. So this is the second video in part one. So in this video I will be introducing the case study that we will be using for the rest of this tutorial, and it's the case study that motivated like this tutorial. It's a case study. We will use one of the output of Earth system models, which is sea surface height. From sea surface height, we're going to learn something about loop current, which is a current like an ocean current in the Gulf of Mexico. And from the loop current position, we will learn something about red tide. And I will like red tide in Florida. This red tide it's a harmful algae bloom that occurs in the west coast of Florida. And it has a lot of very adverse socio-economic implications, which I will talk about. Okay, so the outline of this presentation, I will first talk about application, traditional and application of Earth system model. Then I will talk about regional Earth system modeling, traditionally how this has been done, and then I will talk about something new that is happening right now, which is high resolution Earth system models and the ESMIP 6 high resolution MIP. And for more details, if you don't know what is ESMIP 6 or high resolution MIP, you can check the first video of part 1, the previous video. Then I will talk about our general research question, which is can we use an Earth system model to manage a regional environmental problem like red tide, for example? Then I will introduce the red tide problem, and then I will come to the specific research question, what the specific research question we want to tackle and answer in this research. Then I will present our benchmark problem and method, and finally I'll provide an overview about this tutorial, which will and the next videos that will come. Okay, so I mean Earth system model or climate model, which is special class of Earth system model, have been widely used in water resources management. For example, precipitation. This model can simulate precipitation, which is one of the most important factors for water resources management. Earth system model is also used to simulate the global groundwater table, and this also has some implication on global groundwater sustainability. So that could also be another application in water resources management. Sea surface height, that's important in coastal management and coastal engineering to see the impact of climate change on sea surface height and sea surface rise and similar topics. Then Earth system model are also used to simulate extreme weather events such as heat waves, cyclones, and heavy rainfall, so on and so forth. So these are some of the application of Earth system model or special class of climate model. And traditionally this has been done regional Earth system model. How did it happen? So for example, you see here, this is you have a global climate model, global circulation model, a global climate model. And this is regional observation data. So here, this is example for precipitation in millimeter per day. And so this, traditionally, you have this global climate model. This was, the resolution was 1 degree by 1 degree. So it's 100 kilometer by 100 kilometer about. And then how to go from here to here, to the regional climate model. What has been done generally is downscaling, whether statistical downscaling based on some statistical relation, or dynamical downscaling, using a modeling approach, and then you can get something like a regional climate model or a regional Earth system model. So for example, here You have this regional climate model, an ensemble of 12-kilometer grid spacing, and this global climate model, like shown here, is on 150-kilometer grid spacing. Okay, and this simulation period is over like about like a 30-year period. Okay, so this just like what traditionally used to happen, but what is happening now is something different, because what's happening now is that like this climate model or this Earth system model in CMIP 6, they started to have like raw resolution. So for example, like here, this is like a CMIP 5 type of model, like where you have like this low resolution on like by like 0.1 degree to 0.7 degree, for example. Prototype of like CMIP 6, where you have a 0.25 resolution, like this medium resolution, and like you see here the medium resolution. So this is Atlantic Ocean, and here like to simulate the North Atlantic current and the loop current here in the Gulf of Mexico. It will be somewhere here, so the Gulf of Mexico is somewhere here, and you see that it starts to have like a variable resolution. So here in the deep ocean you have like a high resolution, but when near coastal, like you have a coastal refinement. So for example, if we look here, this is the Gulf of Mexico, you have like a resolution of about 15 to 10 kilometer resolution, and then this is the high resolution MIP of the CMIP 6. So this is one of the activities of CMIP 6. So this is the CMIP 6 standard like entry card to CMIP 6, and this is and by the way, not all like CMIP 6 has like experiment like or activity has this resolution. Like some of them would have like the typical like 1 degree by 1 degree resolution, but the high resolution maybe you have like this 0.2. You have like, so you see more refinement and more higher, and even like there are some frontier model where you go to 0.1, where you can get a resolution of 5 kilometer, which is like very fine. So this is an AWI model. It's a German model, and this study you can read it in the geoscientific model developed, published in 2019. Okay, if you want more detail about like high resolution, maybe you can check the first presentation. Okay, so our research question is, can an ensemble of high resolution Earth system model be used to manage regional environmental problems such as like the red tide? So basically, it has two components, like at a regional spatial scale. So we like at that spatial scale, can we resolve the regional phenomena that we are interested in, like loop current? Can this model like resolve like local eddy and like simulate the loop current, for example? But even if it does, what about like we are interested, for example, in a monthly time scale. So what about temporal agreement? Because these experiments, they run for a very long time. Like the historical experiments of CMIP 6, it runs from 1850 to 2015. The high resolution MIP, it runs from 1950 to 2015, like December 2014, both of them. So can we have like a monthly temporal agreement, because what the model simulate and what we observe, like sea surface observation. So that's like our general like research question, and like to answer this general research question, we will apply to the red tide problem. So the red tide problem, that's like a harmful algae plume. It causes massive fish kill, it poison shellfish, it harm marine birds and animal and sea turtle. It affects human race, cause some respiratory and like eye and skin irritation. And of course, it doesn't look nice. So it impacts tourism industry and recreation activity, among like other economic impact. So here, like you can see an example like of this red tide. And what causes the red tide? We still don't know exactly. So the exact natural and potential anthropogenic roles that result in red tide plume outbreak are not well understood. So they're still not well understood, but One of the current working hypotheses is that the loop current location can be a first predictor. So based on the location of the loop current, we can see whether like a Carina Previs Plume event will occur this season and will not, as I will be showing later. Okay, so what do we want to do? Like, so red tide cannot be prevented, and because it's a natural phenomenon, it could like the anthropogenic effect could increase, like could affect red tide occurrence, but it's a natural problem, so it cannot be prevented, but it can be managed and treated. So we have like as an Earth system model simulates the historical and future interaction of the atmospheric, land, ocean, and river component of the Earth system. This can serve as a valuable tool to advance our scientific understanding about like the main driver of red tide and accordingly assist to manage red tide by developing an Earth system-based tool for managing red tide, ESMRT, for example. So this tool, ESMRT tool, can forecast or hindcast the occurrence of Carina Previs Plume, and this will like with respect to management, it has at least 3 management implication. Like it can serve as an early warning system to see like when are we might expect like red tide to occur, and it can help to assess the environmental and socio-economic impact of red tide. So by knowing like how many red tide events are we expecting in the future, and the frequency of red tide occurrence and their scales, and this is like can be good for regional environmental and socio-economic planning, and we can understand the impact of climate change and red tide. So we can study red tide under different climate scenarios and see how different climate scenario will affect the frequency and distribution of red tide. So that's a general thing. So a current working hypothesis of the occurrence of Carina Previs Plume in the West Florida shelf is based on loop current and its eddy, such that loop current position can be the first definitive predictor of loop current possibility. So the loop current and its eddy can be detected from sea surface height variability, which is one of the output of Earth system models. So using the benchmark problem of Mays 2015, the main objective of this research are to validate sea surface height output of multi-model ensemble of Earth system models. So we want to see how accurate those outputs, these simulation with respect to the observation data, the visual satellite observation data of sea surface height. We want to study the effect of mesh resolution, like as the mesh goes finer, does this has like, is this has is this a bottleneck, or like mesh like up to a certain resolution, like it should be fine, and then like there could be other like bottleneck to increase model accuracy of our like prediction of red tide and simulation of red tide, and then evaluate the accuracy of reproducing red tide event given the position of loop current. So we just want to like evaluate this accuracy and see how we can improve this accuracy. Okay, so this benchmark problem of May 2015 is kind of simple. It basically tell you, so this is loop current occurring in the northward loop current. Here, this is a northward loop current, and this is a southward loop current. Here, like this red line just show like the continental shelves. This is the area, our study area, where we are like observing the occurrence or non-occurrence of Carina Previs Plume. And based on this study, basically at these 2 segment locations, we have like here these 2 segments, and we want to know whether we have a northward loop current or southward loop current. How to do this is like you get the sea surface height in this north segment minus the sea surface height in this south segment. If it is a positive difference, then we have like this northward loop current situation. If it's a negative difference, then we have this southward loop current situation. And the results of this study are very interesting, because this study observed that if the loop current is in the south position, there will be no plume. So that's a definitive predictive that there will be no plume. If the loop current is in the north position, then there could be a plume or no plume. So that's like that's like the sufficient, it's a sufficient condition for the red tide to occur, is that like this loop current need to be in the north position. So you see here, when for the plume events where this sea surface height, like you have a positive sea surface height, like means you have a northward loop current, this is like where you observe the plume. But when here, like in all the when the loop current was in the south position, there was no plume. So here, like this is a summary table, for example, to show you like when loop current was in the south, there was no plume observed, okay, out of the 16 events. So basically, this is like can be like our first predictors. Like we can use this to like if we can use an Earth system model ensemble, if it can reproduce this sea surface height difference accurately, then we can see like if we are getting south loop currents, this means that this season Carina Brevis is not going to occur, like red tide is not going to occur. If we are getting a positive difference, like a possibility of north loop currents, this means that this season Carina Brevis could occur or could not occur. So we would need like another factor to like determine, to improve like our early warning system for like the Carina Brevis. So like the method is like we will be using 52 simulation from 10 modeling groups, and 10 modeling groups with 15 medium and high resolution models, so Earth system models. And we will be also using 28 simulation from 6 modeling groups and 8 standard resolution model for comparison. So we will have like 52 simulation from medium and high resolution model and 28 from like standard resolution model for comparison. Then we will analyze the model simulation with respect to the north and south location of loop current and compare with the Visio data. So basically we will try to reproduce this data with this model, like this sea surface height data, to see if we are getting like a positive or a negative for each of these events, and accordingly to see how can we reproduce like these numbers in the table. So we will do this for like this data. Like this data is, I think, from the period of 1990 to 2010. So once we calibrate like our ensemble, so we have like a 52 simulation, we will like do a weighted ensemble, like we estimate a model weight for each one to reproduce this data. And once we have this model ensemble, we can use this model ensemble for hindcasting, like to look back where we don't have like a Visio data and like see if we can reproduce the number of Carina Brevis occurrence where or not, like how accurate is our model in hindcasting. And then once we calibrated the model, validated the model, then we can use it for projection with future simulations. That's when we will start to use the SSB simulation of like this Earth system model, as I explained them in like the first video. Okay, so that's our method. So the tutorial outline. Here, like part 1 is covered using an Earth system model. Part 2, it will be accessing the outputs of an Earth system model, like how to search for this data, how to install like Python to use it to download this data, and how to have a quick access to this data and visualize it with Panoply. Then in part 3, I will be showing processing the outputs of this model, like because this model, for example, like once you get the sea surface height data, that would be for the whole Earth, but we are not interested in the whole Earth. We are just interested in the Gulf of Mexico region, so how to clip the data for the region and the time frames that you are interested in. And if this data needs to be regridded, like it doesn't follow like a longitude and latitude grid, and you need to regrid it to longitude and latitude, like how to do this. And then in part 4, I will think about how to visualize the output of Earth system models, and then in part 5, I will say how to analyze sea surface height of Earth system model for like giving this case study, how to estimate sea surface height at a certain location and count the number of Carina Brevis plume accordingly. So this is like an example, for example, standard versus high resolution snapshot in in 2010, in March 2010. So you see like this high resolution model, it can reproduce this low current where like an Earth system model is standard resolution of this model has a nominal resolution of about 10 kilometers. This model has a nominal resolution of about 100 kilometers. So you see this one, it cannot reproduce what we are interested in, for example. And then I will like show you how like to create a time series of like your data at like the location you're interested in, like here as this two segment, and how to have like a confidence interval. So here this is a confidence interval for like multiple ensemble of one model. So you will see like how to do these things. And yeah, and that's the end of this tutorial, of this video, and see you in next video. Bye bye.